Today, I want to share with you some ideas and a case study regarding constructed wetlands as a tool for improved treatment of wastewater, particularly in smaller rural towns. So back in the mid-1990s, I worked at the U.S. Army Corps of Engineers Waterways Extension Center in Vicksburg, Mississippi. I think it's called the Engineering Research and Development Center. But while I was working on my master's degree there, I got the chance to work alongside a few of the big name folks in constructed wetlands at the time and participate in some workshops that were designed to meant to train engineers in the design and implementation of constructed wetlands for removal of different types of pollutants. So I went on to get my PhD at NC State working on improving water quality in agricultural watersheds, and had an opportunity there to study how wetlands could be incorporated into drainage networks to improve or reduce the amount of nitrogen that were coming from these watersheds. So since then, I've been able to work in the areas of riparian buffers and stormwater wetlands and wetland restoration, but only a few years back, with the help of some funding from NC State, the Water Resources Research Institute, and Sea Grant, was I able to circle back around in an attempt to refocus on constructed wetland systems in North Carolina. So what we're talking about here with surface flow constructed wetlands, number one, they're an excellent example of ecological engineering. You heard Dr. McDade just a minute ago talk about an ecological definition of sustainability, and that's really what ecological engineering is about. It's developing, designing, and implementing systems that integrate the environment and human society for the benefit of both. So we're really on the same page there. As a matter of fact, as a National Society of Ecological Engineers, and the last national meeting we had actually was in Asheville, and it was one of the most successful ones that we've had. So the ecological engineers have been in Western North Carolina, and there's a few that are working there in stream restoration, stormwater, et cetera. But the wetlands that I'm focused on right now are the surface flow constructed wetlands, which are most similar to emergent macrophyte wetlands, kind of shown in this picture right here. You know, about a foot of water in these areas with herbaceous plants suited to take high pollutant loads and high hydraulic loads. What makes them special, in my opinion, is that they use natural energy sources, low fossil fuel inputs, and they're generally low maintenance, but not no maintenance. And that's something that I hope that you take away from this talk today, as we'll expand on a little bit later. They have high plant and microbial activity, a lot of carbon in there, and they have aerobic and mostly anaerobic zones there that promotes nitrogen removal from both plant uptake and microbial activity. And what we're talking about right here is transformations and removal of nitrogen through the processes of nitrification and denitrification. These systems are typically best at polishing wastewater that has been pre-treated somehow. So you're not putting full strength municipal or industrial wastewater in these systems. Mainly they've been polished or pre-treated somehow. So I think I've made a pretty good case about, you know, them being a pretty good technology for wastewater treatment. And so if they're so great, they should be numerous in North Carolina, right? Well, that's what I thought. But we did a survey, and we could find 5 of these operational in North Carolina. 5. I was shocked. You know, if you look in the literature in California and Florida, I mean, they have hundreds of these things. And the climate here is not that much different as far as temperature-wise. So, so it is what it is. And so as we started down this road, we found out about these, visited with the people that ran them, and learned a little bit more about them. They were mostly used for wastewater. There is that one in New Hanover County that was landfill leachate. one in Aurora, one at Walnut Cove, which is up in Stokes County, which is getting toward western North Carolina, one at the prison there in Halifax County, and one in Goldsboro. But what I want you to notice here is that they're fairly big, but not too large. What I want you to notice there is the year that they were built. Most of these are nearing 20 and 25 years old. And so, you know, of course, that raises the question, why haven't more been built since then? And then in surveying and talking to a lot of these operators, we found out that very few have both inlet and outlet flow and water quality data. See, it makes sense. A lot of these towns are running on really low budgets, and so they're really just concerned on whether or not they're meeting their pollutant permits for nitrogen and organics and total suspended solids. So they don't really care what's coming in there as long as they know that what's coming out is meeting their permit. From somebody who wants to study and promote constructed wetlands, that's a barrier, because I can't tell how well these things are actually treating the wastewater since I don't have that inlet data information. So my motivation here with this work is to try to demonstrate that constructed wetlands are a technology that could be added back to the water quality toolbox, particularly for rural towns. And when I say rural towns, a lot of these towns have low budgets, but they also have small populations and low flows. And so constructed wetlands would be better in that type of situation than maybe, you know, trying to polish wastewater coming out of the wastewater treatment plant in Raleigh. And so, you know, there's rural towns that need additional nitrogen treatment to meet their permits, either because they are in need of expansion, maybe they have a population increase, or maybe the nitrogen permits that they are going to have to deal with are getting stricter and stricter. So thinking about these constructed wetlands as kind of an add-on. And excuse me. One of the things that we've noticed is that the tertiary, or the kind of the polishing treatment of wastewater from package plants, constructed wetlands would be really good to polish the nitrogen species that is produced in these package plants. This is a package plant that was actually at Pilot Mountain State Park here. And this, among with other small facilities that have either extended aeration or activated sludge, the way that they work is that they convert ammonium into nitrate through nitrification. And so what's going on is that many of them can treat ammonium that's coming through there that is 20 milligrams per liter, which is fairly high, to less than 1 and meet their permit. Because the permit is written to keep ammonium, which is directly toxic to aquatic organisms, to keep that low. But what they do in the meantime is that conversion of ammonium to nitrate through nitrification is almost 1-to-1. And so they're still exporting 15 to 20 milligrams per liter of nitrate nitrogen. So that still contributes a lot of nitrogen to our streams. So 50,000 to 100,000 gallons per day, every day, at 20 milligrams per liter nitrate is quite a bit. And so thinking about putting these constructed wetlands downstream of these package plants when there's generally enough land to do so, could be a way of reducing those loads to our streams. So we entered a partnership and got some funding from WRI to demonstrate the effectiveness of the Walnut Cove constructed wetlands up in Stokes County that would help other rural towns in North Carolina meet or exceed their wastewater permits. Basically to give them a case study so they would understand what towns who have this, what they have, how they could operate, and then try to promote this for other towns. And so this is a picture from this pretty innovative at the time wastewater treatment facility, where the wastewater comes into 2 lagoons. You see 1, 2, comes into lagoons 3 and 4. It passed through a duckweed raceway, which was a shallow lagoon there that was intended to use duckweed to take up some of the nitrogen, the residual nitrogen. And then that water that was hopefully converted most of the ammonium to nitrate would then enter the anaerobic wetlands, mostly anaerobic wetlands, to pass through there, reduce the amount of nitrogen, more biological oxygen demand, and then discharge into a chlorinator, dechlorinator for final bacterial removal. And so we started this. We made the assumption that this, looking at the permit records, that this thing was functioning as designed. And so it would be a great demonstration place. Again, if you look at the circles here, and the circles, the size of the circles are the relative abundance of each one of the nitrogen species. Most of the wastewater comes in mostly as ammonium, just a tiny bit of nitrate. As it makes its way from the lagoons into the duckweed raceway, the ammonium drops, the nitrate goes up. When it enters into the wetland cells, the nitrate is higher with just maybe 25% ammonium, and then both nitrate and ammonium come out at very low quantities and concentrations before it enters the chlorination or disinfection mode. So as I said, that was our initial goal. This graph here shows that the Walnut Cove permit for a BOD5, which is the organics, and total suspended solids were 30 milligrams per liter, and ammonium was 10 milligrams per liter. And all of those bars running from 1996 through 2008 shows the mean concentration, mean yearly concentrations of all those constituents coming out. So there's a few photos there. Wendy Hardup from the town of Kernersville came out and visited. You can see how big the cattails are. On the bottom right there is my current PhD student, Brock Kamrath, who has collected the lion's share of this data, and a former PhD student, Jack Kirky Fox, who helped at least initially collect some of the samples and do some of the instrumentation at the site. So this is what the monitoring looks like. This is 2 cells, about 4 acres total. The cells were about 60 feet wide and about 1,200 feet long. Water was split and went into the cells at an equal amount. And we have been doing continuous monitoring of the inlet and outlet flow and water quality, and collecting of on-site weather station parameters, among other things, for a few years now. And so it's an expense. It's not a considerable expense, but it's something that many small towns are not willing to do based on their budgets. So the first thing that we noticed, no, this graph isn't incorrect, but when we started monitoring there, we noticed that the ammonium concentration that you can see there on the y-axis coming out of the wetland cells were actually higher than what was coming in. Let that sink in for just a second. Ammonium coming into the wetland was lower than what was going out. I said that 2 different ways, but the bottom line is it didn't look like the wetland was doing much for ammonium. And also, we weren't seeing a lot of nitrate coming into the wetland. Remember, nitrate was what we really wanted to see the wetland treating, and we still weren't seeing much of that. So that was a red flag on all of our excitement for monitoring this system. Here's some of the numbers here. We were seeing very low numbers of nitrate coming in, wetland 1 out, wetland 2 out. That's each one of the cells. And we were seeing basically most of the time, once it all evened out, about the same amount of ammonium coming out that was coming in. All right. That's not good for promoting wetland treatment with constructed wetlands. But I was convinced we could figure out what was going on here, because that's not the way it's supposed to work. When we dug in a little bit deeper, we saw that this trend of ammonium coming out of this wetland through time has steadily been going up. The red dots there are ammonium concentrations. The yellow line is the permit numbers, and we weren't really seeing a lot of changes in flow. So there seemed to be kind of a steady, almost linear increase of average ammonium concentrations coming out of this system. So, so what we were seeing on the short term there looks like a possible long-term trend at the site. The story gets better, I promise. What we think was going on is that the actual nitrogen cycling at Walnut Cove was that the pre-treatment of ammonium and the conversion to nitrate before it got to the wetlands was not as efficient as it needed to be. And then once the ammonium got into the wetlands, wetlands should be able to remove some ammonium because it has a little bit of minor oxygen areas in it. But it didn't seem to be treating the ammonium at all either. And so basically the water was just passing straight through. So we started observing some things there. This is Brock in at one of the outlets there. And we noticed that almost every time that we went out there to collect data, that there was this excessive detritus and muck layer that was moving its way into our outlets. And it was making us mad because it was clogging our weir outlets and it was messing up our flow calculations. But that was kind of our initial reaction. But what we were seeing there is possibly 25 years of built up detritus from growing and dying cattails and other plants that was moving almost like a glacier out through the outlet, okay? And all of that stuff is made up of organic nitrogen that could actually contribute ammonium. And it also essentially fills up the wetland. So the water depth for this design was supposed to be more like 1 foot of water, and the water was kind of skimming over the top of all of this detritus. So possibly it was short-circuiting through the system, meaning the water was not staying in the wetland as long as it should have or was designed to. So we started doing some pretty cool rhodamine dye tracer studies. We would take this rhodamine dye and inject it into the wetlands, and not only fly some cool reconnaissance drones there to get a pictorial of what the dye looked like going through the wetland, we also set up downstream our water quality samplers to collect samples that could be measured for fluorescence to determine the breakout curves of the dye. In other words, a little bit of that dye starts coming through and then gets more and more concentrated, and you get a curve that you can calculate how long the average amount of water stays in the system, okay? One of the things that you should notice from this picture is these are the two cells. The water was added, the dye was added to both of these cells at the same time. The one on the left shows that the dye shoots through the middle of this wetland until it spreads out into some open water. That happened in probably 15 minutes. And what was going on there is that there was a lot of detritus right there, and these things formed almost little streams through the middle of that detritus, and the water shoots through these areas and doesn't spread out evenly. In the upper right here, you can see that this was after about 4 hours. Look how much further that the water, that the dye has gone, almost halfway through. The leading edge is halfway through compared to where in the other cell where the water was spreading out a little bit more. So that's a pretty good visual demonstration of short circuiting there. And that just means the wastewater is not staying in there as long as it should be, and it's not using the complete surface area of the wetland for treatment. And when we graph the breakthrough, you can see that the majority of maybe you can see this cursor, but the majority of the dye came out of this first cell in about 15 hours and then dropped there. And so once you do the calculations under here, the mean residence time of the water was less than a day. And it was designed for a hydraulic retention time, that's what HRT stands for, of about 4 days. And so the wastewater that we were putting in there at fairly high ammonium and very little nitrate was shooting through the system, and not really, the wetland wasn't really giving itself a chance to treat the water efficiently. So that detrital buildup, that's a picture right there of the amount of detritus that would accumulate over 25 years. About 1.3 feet in this particular location. I think we figured out that on average about a ½ inch of muck was accumulating within these wetlands per year. Now, a little bit of muck is good because that's the carbon that fuels the nitrogen removal processes of denitrification and also gives microorganisms a place to live. But too much fills it up. And so, you know, you get this short circuiting, you get this poor mixing. And like I said, this is organic material in there, you know, much like mulch that was sitting there. It's going to leach nitrogen back into the water column. So whatever treatment that the wetland may have been able to give was actually probably offset by the amount of ammonium that was leaching from the detritus within. And this wasn't the only place. You notice, you know, most of those wetlands were close to 20 years old. In talking to the operators, going to the sites and taking some water quality measurements, we saw similar issues at both Aurora and Caledonia Prison. And, you know, simply put, when you look in the literature, even the textbooks about constructed wetlands, there's not a lot of information out there about how you're supposed to maintain a 25-year-old wetland. You know, people have tried burning the detritus, but, you know, it's kind of spotty on the success that people get from doing that. And like I said, there's not a lot of water quality data out there to either prove or refute those methods work. So at this point, you know, my team and I are thinking, you know, it's going to be pretty hard to endorse these wetlands when the ones that are out there have age-related problems. How are you going to convince? How are you going to show this data and convince a town or, you know, even DEQ that this is a good idea when they're in this situation? So we have to figure out a way to turn the clock back on these types of wetlands, to start testing them again, to show what their removal potential actually is. So thank goodness WRI and North Carolina Sea Grant came through with this community collaboration research grant. It was a small grant, but enough for us to remove the detritus out of one of the cells and document the process of doing it, and being able to test side by side the nutrient removal capacity of a cell that has been cleaned out and essentially reset back to almost back to year 0 compare that to side by side to a 25-year-old detritus-filled wetland. And, so we documented, how we did it. We were able to test the effect of water quality, oxygen distribution, and internal hydraulics through more tracer studies to see how water passed through there after we cleaned it out. The idea was pretty simple. We had wetland that had a lot of detritus in it, very shallow water, low hydraulic retention time, and a high internal source of ammonium. Once we cleaned it out and left some of the cattail in, left a little bit of the detritus there because we didn't want to completely strip it of its microbial community and its internal nutrients and carbon. But by doing this, we're able to achieve a longer hydraulic retention time and a lower internal source of ammonium. So here's the clean out plan. We took the cell offline, allowed it to dry out some, and contracted with a guy who could run an excavator with a 60-foot boom. We worked from downstream to upstream, and we pulled the detritus out onto the banks and allowed to dewater back into the wetland. We left between 4 and 6 inches of the detritus in the cell for that microbial community and carbon. And then one of the coolest things that we did was that as we moved up the cell, we grabbed 4-foot clumps of live cattails and dropped them back in on the areas that we had excavated. And essentially we were replanting as we go. And it only took about 5 days to do this whole 1,200 foot by 60-foot wide cell. And it was about, like I said, about 5-day process. Excuse me. So there you can see cell 1 before. Notice all the detritus in the shallow water there, just when we were cleaning it out. And then afterwards, we gained 8 or 10 inches of more water storage, and you can see the clumps of cattail there right after we did it. And we did this in about in May of 2019. So how well did it work? So we're continuing our research and outreach out there, but we can give you some pretty good information already. So this hook that is coming into the picture right there shows the reestablishment of the vegetation by the fall of 2019. So we completely dug that out and replanted it with cattails that were already in there, and we got nearly full coverage. Contrast that to the cell up above here, where you see all that open water area. That open water area is there because the muck had gotten too deep and the water impounds in there, and it actually kills the cattails off. So this, the way that this cell looks right now is probably the way that wetland cell looked maybe 3 to 4 years after it was initially built. And just another picture of that from the other way. So when we did, this is kind of a ground view of the dye tracer study in that same cell. Over on the left, that's the cell before we cleaned it out, and you can see it starting to short circuit through the middle of the wetland, just like it did in those aerial photographs that I showed earlier. But now you can see what we did, that the dye spreads out across the whole width of the wetland and moves through there using more of the surface area of the wetland for the treatment. And in fact, this graph really shows it, that the number of days in the cell 1 where the detritus is removed is somewhere in the neighborhood of 3 days now, where in cell 2 it's still just over a day. So about 3 times more hydraulic retention time now that we've removed the detritus in cell 1. And so we think that's starting to show up in our water quality data. Wetland 1 is the wetland that we cleaned out, and notice that the water was coming in at about 5.5 milligrams per liter ammonium and going out at less than 4, whereas in wetland 2 it was actually going up to about 6 milligrams per liter. And what that amounts to is that we're starting to see about 27%, about 30% reduction in concentration of ammonium and 23% reduction in concentration of total nitrogen, rather than about flat as we had seen in wetland 2 and wetland 1 before the rejuvenation. So we were seeing concentration starting to fall and the wetland to start working much like it was before, much the way it was designed, aside from the fact that it wasn't getting the nitrate that we were hoping that it was going to get. So what that means when you look at a mass removal during a short number of months, they're less than a year, is that cell 1 was removing about 150 more kilograms of nitrogen than the cell that was not cleaned out. Okay, that total nitrogen removal is 15%, which is better than 0%, but not quite where we wanted it to get, primarily because we're still receiving most of the treated or the pre-treated wastewater as ammonium rather than nitrate. Remember, this is also a polishing step, so we wouldn't expect, anything close to 100% removal either. But that's an extra, 100, just through this period in this one cell, that's 140 kilograms extra of nitrogen. If you were to do that for both cells, you're talking about 300-400 kilograms of nitrogen that's not being exported to, or potentially exported to the Dan River Basin, just by doing this nutrient clean out. So what does all this mean? So for Walnut Cove, the muck removal was a success. They had simple things there. They were as equally as excited that they didn't have to clean out their chlorination basin because of all the muck that made it through the outlet into their chlorination basin was really a pain for them to clean out, and it was affecting their bacterial numbers because the chlorine couldn't contact the water like it was supposed to. They're also exciting that there's less potential for permit violation. They've had a good track record there, but as I said, the ammonium levels were creeping up close to that 10 milligrams per liter. And they're also more confident that the muck removal was worth it. That collaborative grant that we did was meant to do just this: demonstrate to a town that a maintenance or construction project was worth it, and then they buy in and do the other. And in fact, there's plans there to clean out the detritus in the second cell as we speak. Now, for all constructed wetlands in North Carolina and beyond, it's clear that over time, the accumulation of detritus is going to lead to hydraulic inefficiencies and compromised treatment performance. So we can demonstrate that to small towns and say, look, if you don't do this, this is what's going to happen eventually. And we can improve that constructed wetland lifespan by more frequent cleanouts. It might not cost $15,000 to do it if you do a little bit every year, and be able to do and provide better future maintenance plans, whether you rejuvenate the wetland like this or harvest the cattail every year. None of these towns I talked to had any maintenance plans. In fact, if you look at kind of the Bible in treatment wetlands, the book's called Treatment Wetlands. The shortest chapter in the book is about maintenance. And talking to the author said, I said, well, where's your chapter about what you're supposed to do after 20 or 25 years? And author Scott Wallace says, we don't have it yet, but we might be using your information that you get from Walnut Cove and others in that next edition. So there's just, in the fairness to these towns that had have these wetlands, they just didn't have a lot of guidance about what to do. And that's kind of how we've pivoted in this research so far. And I kind of capture that here. The broader impacts here is that the data and the experience that we're gaining right here will provide additional resources for site managers at wastewater treatment plants with constructed wetlands. And, you know, now that we've rejuvenated the wetlands, we've kind of looked into the future of what somebody could expect down the road. We think that we've taken a substantial step in trying to remind towns that these wetlands could be really good for them, and they shouldn't be scared off by the buildup of detritus and these other problems that might be reported, because that can be fixed pretty simple. And like I said, you know, our experience there is being shared with the broader scientific community, could be featured in a new edition of treatment wetlands, and I think could be used in places outside of North Carolina. So, could adding these wetlands to minor wastewater treatment plants improve water quality across the state and even in western North Carolina? Well, each one of these triangles represents one of the 483 minor wastewater treatment plants operating in North Carolina. Many of these are just like those activated sludge systems. They're small communities, small towns, and they don't necessarily have the most rigorous nitrogen permit guidelines right now. And they're discharging nitrogen at a pretty high level. You've probably seen some of these out west. I've seen them at Pilot Mountain, communities near Boone, and they're sitting right on the side of these sensitive water bodies, and I can guarantee you that if I went and collected a sample, that they would be discharging 10 or 20 milligrams per liter nitrogen. Now, it's not as dangerous in western North Carolina as it is down east, but it's still contributing to the overall watershed nitrogen loads. Now, most of these towns are meeting their permits, but I believe that they could do much better than they're doing by putting these wetlands in. These wetlands are not expensive. Many of these places are located in areas where the land is very inexpensive. And so building one of these wetlands, you know, building a 1 acre wetland could be probably done for less than $50,000. And, you know, I won't get into the possibility for nutrient trading and that sort of thing, but there could be ways that these towns could offset some of the cost of that. If a town is growing and they're going to get more of a wastewater load into their system, a constructed wetland could be an alternative, adding that at the end compared to a costly upgrade of an entire extended aerated system or activated sludge system. So I think that they should be, the toolbox should be opened and these things be considered again. And I want to leave you with this. So our best guess is that there's probably somewhere between 80 and 100 stormwater wetlands that have been built in North Carolina. Mitch Woodward, that you'll hear from later, could either confirm or refute that, but that's about what we've calculated here. And these things are great. They help to protect water quality from treating stormwater and are widely accepted. But just imagine if you built these things, an equivalent size treatment wetland to a stormwater wetland, and that instead of just on rainfall events, they could receive wastewater to treat every day. And so I did a calculation here. You know, the stormwater wetlands are event driven. They're generally more expensive to build because they're in urban environments, and they get really small amounts of nitrogen entering into the system. So if you built one that was receiving 10 milligrams per liter of nitrogen and about 50,000 gallons per day every day, look at the difference of nitrogen that you could remove. One treatment wetland could remove about 30 times the nitrogen per year when compared to the same size stormwater wetland. So this is not to say that we shouldn't have our stormwater wetlands, but it's to say if we've committed to building stormwater wetlands, why can't we put more of these wastewater treatment systems in and get more bang possibly for our buck? So at least I think that we should try to get behind more of these systems to put a bigger dent into our watershed pollution problems. So with that, I'd like to thank you again for having me, and I guess I can entertain some questions in the time that we have.
Thank you very much, Mike. That was fantastic, and really appreciate your insights and the great work you're doing. And we have a number of questions that have come in from the audience, and we're going to ask them to you, and we're also going to give others the chance to formulate questions while we're continuing to answer their questions. And this is going to be done by having a graduate student here at Lenore-Rhine, Andrew Polich, and myself asking some of the questions. I think the very first question that was asked, it was before you got it started, and I think you probably answered it through the talk, but I'm just going to read it out. And it was from Joshua Gilman, and he said, "It is my impression that constructed treatment wetlands may have rigid operating and maintenance requirements. Can you confirm, correct, or otherwise clarify?" And I think you pretty much made that point clear, but if there's anything you want to add to that, thinking about the rigid operating and maintenance requirements, that would be interesting.
So the operating requirements are that you know, they've been designed to receive a certain concentration and load of whatever pollutant that they're trying to treat. Let's just stick with nitrogen here. And so the inlets are designed to allow that amount of water to go in, and the outlets are designed to hold the water at a certain depth, generally between 6 and 18 inches, depending on the time of the year, depending on the flow. And the deeper that you hold the water, the more hydraulic retention time you have. That doesn't necessarily always result in better treatment, but doing that allows you some flexibility on, especially if you can monitor the wetland, on adjusting your treatment times. So to me, that's not really rigorous if the operators are trained to do that. However, I've learned that, you know, in these small towns, the public works director is doing everything, and so they're not necessarily watching these as much. However, the more expensive package plants aren't plug and go either, and they're much more expensive too. So you know, the money that you would save in a wetland versus a package plant, you could probably hire 3 or 4 people to go out there and baby the wetland if you wanted to, but you probably only need one to go out and check it at least 1 or 2 times a week.
Great, thanks. Andrew, do you have a question?
Yes, I will ask this on behalf of Sarah Clement. Is there research on ways to enhance natural detritus removal and to reduce the need for maintenance?
So is that question, are there microorganisms that will chomp on that stuff faster? Is that what I'm hearing there?
You could take it as such, yeah.
So the answer to that question is I don't know, and I don't think so. I do know, like in lagoon systems, that there are companies that sell microorganisms that will drop sludge layers by inducing more microbial activity, and that helps lagoons hold more of their water. But what we're thinking about here is almost like the Brooklyn Bridge. You know, once they start painting one side and they get to the end, they start painting it again. What we think that could be the best way of maintaining detritus in these is to clean out sections of cattail as kind of rectangles that are perpendicular to flow, and kind of alternate those through season. And what that would do is not only would it keep you from having to clean the whole thing out every year, but it would also induce an open water area that may redistribute the flow, almost like a baffle, to make the water go across the wetland at these particular times. And also promote a little bit more UV interaction that may kill off a little bit more bacteria, may induce a little bit of algae there to sequester some of the nitrogen in those areas. But that's how we kind of envision it going on. So maybe they go out and spend $1,000 a year to clean out a little section of that, but they do it every year.
Great. Thank you. I'm going to ask a couple of questions on behalf of Michael Malloy, who asked some of these early on in the talk. You were talking about a certain number of days as retention time, and he says, what is the ideal retention time for water in the system? And then he follows up and asks this question, what is the disposal plan for the removed muck to ensure that the removed nitrogen does not re-enter the environment?
Okay, so the first one is the favorite professorial answer is it depends. The hydraulic retention time, there's some models that they're basically empirical models that are based on observation data, and we come up with kinetic removal coefficients for nitrogen. Now, if we want to treat 100% of the nitrogen that comes in there, then we're going to need a really big wetland with a low retention time, or I'm sorry, you're going to need a really big wetland or a small wetland with a large retention time. So there's no like one number. For this wetland was designed at probably the nitrogen, ammonium at about 5 milligrams per liter, nitrate at about 5 milligrams per liter. And during the summertime, the models suggest that would 4 days retention time there would reduce both of those by about 50%. So it depends. It depends on what your treatment goals are. The second question about what to do with the detritus. Great question. What we did with the detritus is that we put it back on the banks. It is cattailed. This is not industrial polluted wastewater. This is water that has just got ammonium and organics and some bacteria in it. So what we did is to put it up on the banks, and this stuff compresses from about that 18 inches down to about 3 or 4 inches as it dries out, and it dewatered down the banks back into the wetlands. So that was essentially where we captured that the runoff from that. Excuse me. We also had that tested just in case there was some metals accumulation in the detritus from whatever else was going through the wastewater treatment system. And none of that, all of that stuff was way below any type of EPA standards. So we think rather than filling up our landfills with that type of stuff, put it on the banks, let it dewater, or look at ways that could actually be composted on site and reused somehow. And that's going to take some a little bit further study and perhaps some more permitting. But everything that I see, that stuff is not dangerous. And it could be actually used as mulch around maybe some low touch areas around a rural town, or even at the site itself, at the wastewater treatment site itself.
Great.
Michael McIntyre asks, one of the limitations we have in the mountains is the amount of available flatland for wetlands. What do you think that there are ways to design wetlands that are more compatible vertically for the land here?
Another great question. I have not worked in what they call vertical flow or subsurface flow wetlands that often, but what I understand is that you could build these things vertically and have like a rock media in them and pass the water vertically through them, and perhaps recycle that water through these systems again and again, so you don't have to have like a half acre vertical wetland. They could be done sequentially. They could be recycled through. But that would be an option, but not an option everywhere. It may become cost prohibitive in those situations. A smaller wetland that you would be willing to maybe make a fossil fuel allowance, you could put a smaller wetland in there and recycle water through a wetland several times if you have a limited footprint in order to try to meet your treatment goals as well.
Very interesting. I think we're getting close to time to wrap up, and we might not get to all the questions, but there were 3 questions or comments about differences between stormwater wetland and a treatment wetland, and is it possible to convert from one to the other, from Michael, as well as there are questions, can you think of scenarios where you would see a treatment wetland and stormwater wetland on the same site? Is rural treatment a limiting factor? I think you commented on that a little bit, but is that question clear?
I see them mostly in 2 different locations. Okay. Just because the stormwater wetlands are not, they don't have to be permitted for discharge, where the wetlands would have, the constructed wetlands for wastewater treatment would have to be. But they could be, the stormwater wetlands could be connected to the wastewater treatment wetlands, perhaps, if the site, if it made sense on the site.
Great. I'm just going to interject with one other question that combines a few questions. There's a question just came in about why was the wetland designed like it was and not more similar to the way wetlands naturally form? Would it be beneficial to have an initial 5-year maintenance period to help the wetland establish closer to a natural wetland? And then related to that, have different plants been considered or studied? Cattails seem to create a lot of waste.
So, so if you were to build this much more like a natural wetland, it would have to be 6 or 7 times as big, because there's not many emergent wetlands that have a foot of water in there all the time. And this is what engineers and ecological engineers have found that will work. There's not a lot of plants that will work as well as cattails in here. Bulrush, Chenoplectus is pretty good. There's studies about how they work together, and it's basically a wash between the 2. I think mixing the 2 species, it could be a good idea, but you're limited. These plants, there's not like a super nitrogen removal plant out there. They go through this luxury uptake, and cattail and bulrush do that about as well as any other. And so I'm a firm believer of sticking with this plant right now until I'm convinced otherwise, and just figuring out a way to control the detritus early on. I don't think it's impossible to do that with some planning.
That's great. I'm going to say, I know there are a number of questions that are still out there, and if Dr. Mike Burchell can still hang on for a few more minutes, we can have him continue to answer those with some text, or maybe even as people take a break. But I want to make sure that everyone has a chance to take a break, because it is now 9:53, and our next talk will start at 10 o'clock. So if you need some water or need to use the water closet, now's the time to go. And we are also going to be setting up our next speaker in the next couple of minutes. So I'll first start by saying thank you very much, and a round of applause that the crowd goes wild. Dr. Mike Burchell just enlightened us with some really interesting information and that great research that he and his graduate students have been conducting. If others have a way, there is some contact information for him here, and we will also engage him in these questions the best we can while others are getting a break. Quick break. Thanks again.
Hey, thank you.
Okay, so I'm just going to say, I don't know if you see the questions, Mike. Do you have a chance to see those?
I do.
Okay. Are you comfortable aiming to answer 1 or 2 of those more?
I'll do my best with the time that I have available.
We only have a few minutes, yeah. So, and if we don't get to all of them, we'll keep a keep a running list here, and we'll do our best to gather information. But Dr. Burchell has a class to teach. He has to run off very soon. So thanks again.
Does this outfall to this particular wetland fall under their NPDES permit? Their permit is at the outlet after it goes through the chlorinator dechlorinator. So that's where they get, that's where their permit falls. All right. And this is actually one of the limitations that I'd like to see done away with. Anytime you discharge from these wetlands right now, you have to chlorinate, dechlorinate it somehow. I would argue that if you had a system that already went through chlorination, dechlorination, and you wanted to add on a wetland at the end, that the bacteria concentrations in the wetland following chlorination, dechlorination would be no different than any other natural wetland. And so I wish I could figure out a way for them to get an exemption on that. And that is a limitation, I think, to more of these systems being added on. Okay, hopefully that answers your question. I answered Michael's question. Bill, do they have combined sewer stormwater system? Not on purpose, they don't, but they do have a lot of I&I, that's infiltration to the system. And yes, there can be dilution into the system when it comes down. And that doesn't hurt concentration treatments, it only dilutes it. But there's not any improvement in treatment from a load standpoint that we notice. $50,000 to construct a 1 acre treatment wetland. No, that's kind of, does that include the design fee? How much did it cost to remove the detritus from wetland 1? Good question. 50,000 might be a little light. I sometimes miss that a little bit because, when we do these designs, I'm pretty much being paid to do these designs. So I'm thinking about the construction of these. However, I think that we can give the design for these should not be that much. Basically you're digging a big hole in the ground. Maybe you have to line it, and maybe you have to design an inlet and an outlet. Pretty simple. I just don't think that, I want to keep these designs simple enough to whether they could be knocked out by even a junior engineer pretty fast. How much did it cost to remove the detritus from wetland 1? About $12,000 to $15,000. Over the life of that system, that's pretty cheap, I think. But I think that they should put in their maintenance budget, willing to put $1,000 into moving that stuff around, some of that stuff around every year, particularly at the outlets.